Alrighty, hi everyone. Welcome to another review session. Thanks for being flexible. I broke my toe yesterday, so a doctor told me to try and stay off of it and not walk on it too much. So I'm just at home resting it right now. So thanks for joining on a Zoom, and I'm sorry we can't be in person. But if you have any questions throughout the Zoom, please just throw them in the chat. You can use the raise hand feature. You can just take yourself off of mute and ask it directly. I want to make sure all of your questions get answered before we leave, so then you have more confidence going into the exam on Friday. Are there any questions for me before we get started? And I know that I posted the homework set early, but I'm assuming that we still want to go over that with me talking it out. Is that correct? Okay, cool. Awesome. Okay, any questions for me before we get started? I'm still going to try and make this so that it's interactive as possible. But I know that it's hard to take yourself off mute and answer in the chat, but I still want to try and ask you questions so that you are probed to think during this. Okay. Alrighty, so we can get started. I did finish practice exam 6 as well, so I will post this along with the recording of it afterwards. And then we'll still have a Zoom review session tomorrow for any last minute questions. Okay, so at the start of homework 6 and practice exam 6, you will have a table of values, right? You will have delta H values and delta S values. These are super important, as you see later on in the homework and later on in the exam. Make sure you're paying close attention to the signs of what you're using. Right, you can see down here in H2O. In H2O, there are gas and liquid. So just make sure that you're looking at what is being used in the reaction and then what corresponding value goes with that for delta H or delta S respectively. But those should all be there. Hopefully that they are all there as needed. But if you think you should have something and you don't have it during the exam, just raise your hand and we'll make sure that we get that value for you. Alrighty. Starting with homework 1, right? For question 1, we're going to start with our true false. And we have some of the free energy from a reaction that is exergonic can be used to do work. Can someone tell me what exergonic means before we even answer that question? Good. Yep, this means that delta G is less than 0, or this can mean that it is spontaneous. Right? If delta G is negative, then we have a spontaneous reaction. Okay, so delta G is less than 0 when it's exergonic. If it's endergonic with an EN, then we have delta G is greater than 0. Okay, so true or false, some of the free energy from a reaction that is exergonic can be used to do work. Yep, perfect. This one's going to be true. As someone else mentioned in the chat, right, delta G is less than 0. That means we're going to release energy. So that energy that is being released can be used in a different reaction. Awesome. Okay. Question 2. The first law of thermodynamics states that the energy cannot be converted from one to another. Is that true or false? Why is it false? I agree, but why is it false? Someone tell me why it's false. Yes, awesome. Right, energy cannot be created or destroyed but we can be converting between different types of energy, right? You can have mechanical energy, you can have potential energy, you can have kinetic energy, right? All of those could be converted from one to the other, but it cannot be created or destroyed. Awesome. Question 3, the heat generated by a system can only be used to do work if there is a temperature gradient. True or false? Yep. Question 3 is true. You need to have a temperature gradient in order for the reaction to flow. It doesn't need to be a super large gradient, right? It can be something different or something small in difference, but you tend to think of something that's very hot going to something that's very cold, and that temperature difference will allow for work to happen. Okay. Anything on questions 1 through 3 so far? Yep. So that just means if you think about if you have a hot cup of coffee and you put an ice cube in it, your cup of coffee and your ice cube are at different temperatures, right? Your cup of coffee is going to be hotter than your ice cube. So energy will flow from that hot coffee to your ice cube. So it's actually warming up the ice cube, and that temperature gradient of something being hot and something being cold will allow for work to happen. Does that help answer your question? You can think of it as like a difference in temperature. Sweet. Okay, question 4. State functions like enthalpy are only defined for standard conditions. True or false? Good. This one is false. You can have non-standard conditions, right? Our STP is run atmosphere 25 degrees Celsius. Standard temperature and pressure, right? So there are times when that does not exist. You can have non-standard conditions, and those would just allow for, or just those would result in either different H values, different S values, whatever you're working with, but those are still state functions. So they would still only matter on the start and the beginning of that reaction, and it does not matter on the pathway to get there. So that state function still applies no matter what. If it's a state function in one case, it'll be a state function in another case. And state functions means it's path independent. Okay, question 5. The greatest work efficiency for a reaction occurs when it is reversible and at equilibrium. True or false? Yep. Can someone tell me why it's true? Yeah, that kind of plays a little bit into it, delta G being at 0. Right, work efficiency is how you are able to convert one type of energy to the other. So if your energies are flowing at 0, if your delta G is at 0, that means there's no additional free energy. And so that means that all of the energy that's being created is going towards the forward reaction, and all the energy that's being, or not created, all the energy that's needed to produce the forward reaction is being used in the reverse reaction as well. So it's almost like, right, if you pull, I pull, and so that work efficiency is going to be greatest that way. And all that fun stuff there. I think that's mostly just a definition type of thing, but you just can think about it going equal and opposite in reverse reactions. And that would allow for the greatest work efficiency. Okay, question 6. The criterion for which a reaction occurs spontaneously is that the delta S of the system is greater than 0. True or false? While you're answering that, equilibrium is efficient just because everything that's happening in the forward reaction is happening in the reverse reaction. And so like nothing's really being created or destroyed in terms of like products going to reactants or reactants going to products. And so it's efficient as in it's like steady. It's steady and it's not changing or fluctuating. And yes, question 6 is false. Spontaneous reactions are determined by delta G. And if a reaction is spontaneous, delta G should be what? Good. Delta G should be less than 0. Okay, any questions on 4 through 6? Okay. Question 7. Spontaneous reactions would violate the second law if the entropy change of the system were negative. Question 7 going to be true or false? Good. Question 7 is false. Why is it false? I guess what is the second law of thermodynamics? What does that tell us? So the second law of thermodynamics tells us that the entropy of the universe is always increasing. Yep. So second law states that entropy of the universe is always increasing. So in order for the entropy change of the system were negative, right? This does not mean that it's violating it because it's just looking at either the system or the surroundings. So if the system were negative, that means that the surroundings is positive. And if the surroundings is positive, that means that the universe around it, systems plus surroundings, right? Surroundings is positive, that will increase the entropy of the universe. And so it would actually support this. There are also cases where sometimes the delta S is negative, but you still have a spontaneous reaction because you're contributing more to the disorder or something else is happening to disorder and increase the disorder of the universe. Okay, does that make sense why 7 is false? Doing the practice exam today and thinking that my life was very chaotic. So like contributing to entropy. Yep, so it could be positive. The delta S being positive. So if delta S is greater than 0, this means that we are increasing entropy. Okay, we're increasing disorder. So the second law of thermodynamics states that entropy of the universe is always increasing. So the delta S of the universe is always greater than 0, right? We're always getting more disordered. So if the system was negative, that means that, right, if we're looking at systems and surroundings, that negative entropy change, that decrease in disorder, had to result in an increase of disorder in someplace else. So if it's not in the system, it has to be in the surroundings. And the surroundings contribute to the overall universe disorder. And so if the surroundings is positive, that means we're increasing the disorder of the universe as well. So that's why it doesn't violate the second law. Does that help answer your question? No, Ethan. So the system and surroundings cannot have the same sign, because if the system is getting more disordered, that means that the universe had to be less disordered. Same thing where it's like the system and the surroundings can never have the same delta H value. If the system is heating up, that means that the surroundings had to cool down. Yep, Adrian, yep, we could say that in order to make this true, we would say the spontaneous reactions would not violate the second law if the entropy change of the system were negative. Perfect. Anything else on 7? Alrighty, question 8. Work is a macroscopic property of the system. True or false? Yep. Yep. So macroscopic properties are like big picture properties, right? Temperature, pressure, all that fun stuff. And work is a part of that big picture kind of idea. So this is just a definition that you need to know. Okay, and lastly, question 9. If the initial number of microstates for a system were 100 and the final number of microstates for after reaction were 15, the change in entropy would be negative 2.62 times 10 to the negative 23. True or false, and how did we determine that? Yep. So the Boltzmann equation is going to be S is equal to K ln of W. And how do we write W? W is going to be a fraction of what's on top, initial or final. Yep, this will be final over initial. So S is what we're solving for here, right? The entropy is this. So we're looking for what S value is. K is a constant and it is given to you at the top of your page. So we have 1.38 times 10 to negative 23. And then we have the ln of, if the system was at 100 and is now at 15, which one is our final? Yep, our final would be 15 over 100. And we do end up getting that S is equal to negative 2.62 times 10 to negative 23. Oops. So this would be true. Any questions on our true false? Okay, moving on to question 10. Which of the following statements involving thermodynamics is or are correct? Okay, so again, just still treating these like true or false questions. So for 1, if a system loses energy, the surroundings gain exactly that amount of energy. Is that going to be correct or incorrect? Yep, this one's still true. right? We think about this as being equal and opposite. Right, and like I said a couple minutes ago, right, if the system is heating up, that means that the surroundings had to be cooling down. So they have to be opposite of each other, but they will be equal and opposite of each other every time. Question or statement 2. The second law of thermodynamics states that the heat flows spontaneously from a hotter region to a colder region. Yep, this is true. We want to follow temperature gradient. And as we're flowing from hot to cold, we're saying that that cold object is heating up and getting more disordered. And that's why it is contributing to the second law of thermodynamics. Okay, and then question 3, a macrostate is a very large state of the system. Yep, this one is false, right? A macro state is like your pressure, your temperature, your volume, that fun stuff there. Right, it's talking about macroscopic properties. Okay, so if 1 and 2 are correct, that means that B is going to be our answer. Any questions on 10? Alrighty. Question 11. Which of the following statements are correct? For question 1, we have the entropy of any molecule is greater than 0 at all temperatures above 0 Kelvin. Yep, this is true. At 0 Kelvin, you have no molecular motion. And so at any temperature above 0 Kelvin, you will have some sort of molecular motion, whether that's 0.1 Kelvin, right? They're going to have some sort of little vibrational motion. And as you get higher and higher and higher, that's when you start to get more into your liquid or gaseous-like particles. But 0, you have absolute 0, nothing is moving. So anything above that will have some sort of kinetic energy, some sort of motion. For 2, if delta G of the reaction is equal to 0 and delta G is not equal to 0 for particular conditions, the reaction is at equilibrium under those conditions. So right, we're looking at delta G at standard temperature and pressure, and then we're looking at G at non-standard temperature conditions. So at those non-standard temperature conditions, if delta G does not equal 0, is that at equilibrium? No, this is not. This is false. Right, if we were at these conditions, then reaction is at equilibrium. Okay, and then question 3. The entropy of a gaseous water is greater than that of a solid water. Is that true? Or entropy of gaseous water is greater than the entropy of solid water. Yep, this one's true. Right, gases always have more entropy than solids. Right, gases are moving around more quickly. They have greater kinetic energy, they have greater motion, vibrational, rotational kind of energies that all contributes to the entropy, and where solids are stuck in one spot. And yes, so for statement 2, if delta G naught is equal to 0, then you would still be at equilibrium. Yep. Okay, so for this particular question, 1 and 3 are correct, and so C will be your correct answer. I'm going to give myself a moment to turn the lights on. So for statement 2, they're saying if delta G of the reaction is equal to 0 and delta G of the reaction at non-standard conditions is not equal to 0, right? So we have standard conditions, it's at 0, but at non-standard conditions, it's not at 0. Then we're saying at those non-standard conditions, is it at equilibrium? This is false because the only time that the reaction is at equilibrium is when that delta G is equal to 0. So in order to make this a true statement, you could either say if delta G of the reaction or delta G naught of the reaction is equal to 0, then you're at equilibrium. That would be true. Or if delta G at standard conditions is equal to 0 and delta G at non-standard conditions is equal to 0, then you would be at equilibrium. You need to have delta G equal to 0 in order for it to be at equilibrium. Does that answer all of the questions in the chat that just popped up? Okay, perfect. Okay, lovely. Question 12. If delta G naught is equal to negative 67 kilojoules per mole for the reaction as follows, at 25 degrees Celsius, find delta G in kilojoules per mole for the same reaction when you have certain conditions at equilibrium. And you also have 2.31 grams of solid sulfur at equilibrium at 25 degrees Celsius. Okay, so usually we're saying that we're saying our standard conditions. But now we're looking for delta G at non-standard conditions. Okay, how do we solve for delta G here? What equation do we have to use?
Delta G equals delta G standard plus RT ln Q.
Does anyone know? Adrian, were you just speaking? I didn't hear you.
Are you able to hear me now?
Yes, I can.
Okay. Delta G equals delta G standard plus RT ln Q.
Awesome. Okay. So in this this equation here, we have delta G non-standard. We have delta G standard. We have R, which is our universal gas constant. What R value do we use for this equation?
0.314.
Yep. T is temperature. And Q is going to be equilibrium constant. Okay, so in order to solve our question here, what do we need to solve first? We need to know what Q is. How do we solve for Q? Are we given all of the values for Q that we need? Yep, we are. Okay, so looking at our reaction in yellow, what's going to go on top based off of the values we're given in the question? Yep, it's still going to be products over reactants. So their first product is sulfur solid. Does that go into our Q? Nope, the solid does not go into your Q, so you're just going to use your H2O. So we'll start off with 3 times 10 to the negative 4. And do I need to add anything to that products portion? Yeah, close, Ethan. But yes, we do need to square it, right? Not a coefficient of 2, but we need to square, because it has a coefficient of 2, we square it instead. Okay, so then on the bottom is going to be our reactants. So then, right, the H2S will also have a square component because that has a 2 in front of it. So this would be, and this would be for your products and reactants. Okay, and then Q here actually comes out to 9. Okay, and then we should be able to plug in everything else that's given to us from our question. So we're looking for delta G. This should stay just as delta G. What's the difference between delta G standard and then R here, though? Yep. So your delta G is in kilojoules while your R is in joules. So I tend to make everything into joules rather than trying to convert everything into kilojoules. So I would say this is negative 67 times 10 to the 3 joules over mole. Plus your R value, we said was 8.314 joules over mole Kelvin. What temperature are we using? Yep, it should be 298 Kelvin. And then we have the ln of 9. And we should end up with delta G equal to negative 61556 joules. So then if you want to put it into kilojoules, this is negative 61.6 kilojoules, which is E. Okay, any questions on 12? This seems pretty straightforward on how to do this type of problem. Giovanni, it asks for your reaction in kilojoules per mole. So that's why I converted it back to kilojoules. I tend to, no problem at all. I tend to convert everything into joules rather than kilojoules. I prefer to work with larger numbers rather than potentially decimal numbers. Right, I have a much easier time working with a lot of zeros rather than 0.000, I guess. That's just how I like it, or I like to say, times 10 to the third. I like using positive numbers rather than negative numbers, so I wouldn't say times 10 to the negative 3. It's all just a comfort and preference kind of thing. Your answer is asked for in kilojoules, so if you like to save your steps, right, that if you convert everything to kilojoules first, then your answer comes out in kilojoules directly. You don't have to go back to kilojoules from joules, but it's really just a personal preference. You just have to recognize which one you have to change if you are looking to do that. Sorry, that's not a very straight up answer, but any other questions on 12? Question 13. What is the standard free energy for the reaction C graphite plus 2 solid goes to CS2 in kilojoules per mole? Can someone tell me what we need to do for this one? Or I guess, what letter are we solving for when we said we want to find the standard free energy? Yes, yep. So for standard free energy, we're looking for delta G naught. Yes, perfect. Yep. So delta G naught would be equal to delta H naught minus T delta S naught. Perfect. Okay, so we're not given a lot from our question. How do we find? Right, we're looking for delta G, so we need the delta H, T delta S. How do we find that information? Yep, we have our chart from the start of our homework. So I know it's a lot easier for me to do this on my iPad than like on your exam, but for ease and whatever, I'm going to write the equation. And then I'm just going to copy this and bring it up to the chart. On your exam, I would recommend ripping your chart off if it doesn't have something. I would just, if you want to rip it off, you can rip off your chart and then you can look at it directly next to each other. But I'm going to create one where we have a delta H. I'm going to write all the delta H's for my products and reactants. So C graphite is at the very top. Delta H of formation is 0. For 2S, that's down here a little bit. Right, that's going to be sulfur solid. That is also 0 because we're looking at that first column. And then CS squared is somewhere around here, right here. And that's 116.7. Okay, keep in mind that these are all in kilojoules per mole when we're talking about delta H. Okay, we're going to do the same thing for delta S. Delta S is hardly ever 0, right? Because we're only, if it is greater than 0 degrees Kelvin, it'll have some sort of molecular motion. It might not be a lot, might not have a lot of disorder, but it should have something. So for C graphite, we have 5.6. For S solid, we have 32.1. And then for CS squared, we have 237.8. Okay, and those are going to be our values for delta H and delta S. So I'm going to bring this back to my question. Okay, and what do we do with those values now that we have them? Not add all of them. We're going to multiply by some coefficients. Yes, we do need to do some adding. Does anyone know the general formula that we're following?
The summation of the products minus the summation reactants.
Yes, perfect. Yep. So we'll have the summation of delta H product minus the summation of delta H reactant. And that's going to be the same for both delta H and delta S. So just change if it says delta H or delta S, doesn't really matter. Okay. So we can have for this one, this would be products come first, and you're going to multiply by any coefficient you have. So there are only one CS2, so this would be 116.7 minus the sum of 0 from the graphite and 2 times 0 from the sulfur. So we end up with delta H of 116.7 kilojoules per mole. Questions how we did delta H? Okay, for delta S, it's going to be the same thing. Again, we're still doing our products first. So we'll have 237.8 minus the sum of 5.6 plus 2 times 32.1. And we get 168 joules per mole. Any questions how we solved for delta H and delta S? Okay, so now that we have both delta H and delta S, we can plug that into our original delta G problem. So we have delta G naught is equal to delta S, we said was 116.7. Again, this is kilojoules per mole. So I'm going to say times 10 to the third joules over mole. Minus our temperature. What temperature are we going to use? What temperature is this? Yep, perfect. Excuse my yawn. And then we have 168 joules over mole. So without even plugging this into our calculator first, when would this reaction be spontaneous? Always, never, high temperatures, or low temperatures? Good, right? This one would always be spontaneous at high temperatures, right? At lower temperatures, it wouldn't be spontaneous. So it's conditionally spontaneous at high temperatures. So delta G naught here becomes 66636 joules per mole. Then we convert this to kilojoules. So this is 66.6 kilojoules per mole, which is B. So is this reaction spontaneous at 25 degrees Celsius? No. Nope, this reaction is non-spontaneous at this condition. No, Julia, everything is not always spontaneous at high temperatures. We could have a scenario. I don't think we have an example. Actually, yes, the next question is an example where it's spontaneous at lower temperatures, actually. So hold off your question for 1 second. Any questions on question 13 before we move to 14? Okay. So for question 14, this is going to be very, very similar to question 13 that we just solved. This time our reaction is NO gas plus O3 gas forms NO2 gas and O2 gas. Okay, so we just have a couple more products and reactants here. One thing to always check is to make sure that you have a balanced reaction. You have 1 nitrogen and 4 oxygens on both the left and the right, so this is good to go. So again, same thing. We need our delta H and delta S for both of these. we have delta H is going to be NO gas is 90, O3 is 143, NO2 is 34, and O2 is 0. And then delta S naught, NO is 211, O3 is 239, NO2 is 240, and O2 is 205.1. Any questions how I got those values and where they came from? Does that make sense how we use the chart? Okay, so again, same thing. We're going to do delta H. We're going to do our products minus our reactants. So we have 0 plus 34 minus the sum of 90 plus 143. Right, our reactants are going to have a higher summation, making our overall delta H negative. So this ends up in negative 199 kilojoules. And then delta S, again, same thing. And we end up with negative 4.9. Right, so in contrast to the question we just did in question 13, right, we had a positive delta H and a positive delta S. In this case here, we have a negative delta H and a negative delta S. When delta H is negative, that's exothermic. The world prefers exothermic reactions. So that's a favorable reaction in terms of heat, right? For delta S, we have a negative delta S. The world prefers a positive delta S. So in terms of entropy, right, we have an unfavorable reaction. So if you have a favorable and unfavorable reaction, we're going to be competing for delta G. And at different temperatures, delta G will end up negative or positive. So for delta G here, we have delta H naught minus T delta S. The equation still stands. Delta H is negative 199 times 10 to the third joules. We are again at 25 degrees Celsius, so this is 298. And negative 4.9 joules. Right, so Julia, if we're looking at values here, right? If we have negative 290, or if we have 298 times negative 4.9, that ends up in a negative value because we have a positive times a negative. That results in, right, delta H minus a negative number, which turns into plus, right, plus whatever. That turns into a positive. Is the word I was trying to say. So if it's a negative and then plus a positive, we want to make sure that our delta H is high enough and our delta S is small enough where we can still have a negative value for delta G. So at those lower temperatures, right, when it's maybe only 5 degrees Kelvin or 10 degrees Kelvin, then this reaction becomes spontaneous because the delta H is so large for that one that it overcomes the change in entropy. So in this case, delta G naught is equal to negative 198 kilojoules after you change it back to kilojoules. So you see that we have a spontaneous reaction because 25 degrees Celsius is considered a low temperature here. Do we see the difference there, right? If we bumped this up to, let's say, 200 degrees Celsius, right, then our positive delta S portion of the equation would be larger than our negative delta H portion of the equation. And therefore, delta G would end up positive rather than negative. Any questions? Are we confused? Are we lost? Are we okay? Thumbs up in the chat for okay. Gigs all around. I kind of hate not seeing your faces. I like teaching in front of people. Okay, 2 more. Question 15. We have find S naught in units of joules per mole Kelvin for the reaction CO plus 2H2 goes to methanol. Can someone tell me how we're going to solve this question? Yep, so we can still use the chart, right? We just did this 2 times in question 13 and 14, but this time we're just trying to solve for delta S. We don't need to find delta G or delta H. So we can I don't know if I grabbed everything. We can copy all of this. Go use our handy dandy chart. Right, we're looking for delta S, so we just need that right-hand side. So for carbon monoxide, we have 197.7. For hydrogen, we have 130.7. And for methanol, we have 127.2. Okay, and then we can solve for delta S the way we just solved for delta S in the previous 2 questions. We're going to do the sum of our reactants minus the sum, or sorry, the sum of our products minus the sum of our reactants. So delta S naught would be 127.2 minus the sum of 197.7 plus 2 times 130.7 because we have a coefficient of 2 in front of our H2. And we end up with delta S naught equal to negative 332 joules per Kelvin. Questions on 15? Okay, and then our last question on the homework. Question 16, we have an exothermic reaction occurs in which delta H of the reaction is equal to negative 250 joules per mole. And during the reaction, the surroundings do work on the system, totaling 100 joules per mole. The change of the internal energy of the system would be question mark. Okay, so can anyone tell me what equation we need in order to solve this problem? Yes, awesome, right? We have delta E is equal to little q plus W. So in this equation, delta E is going to be our internal energy. What is Q? Yep, Q is heat. And what is W? Good. W is work. Okay, so we're looking for the change in internal energy. So we don't know what delta E is. Okay, we're given Giovanni, it doesn't really, so it depends on how you're, I think, looking at the system and surroundings. I tend to work with Q plus W, and then you're looking at the system. So you're saying, okay, what is the system doing and for Q, and what is the system doing for W? Yes. Yep. Exactly, Maya. Yep. And right, well, you might see this as we go through the question. Right. So we have delta E is what we're trying to find. Q is heat, but we're given delta H of the reaction is equal to negative 250 joules per mole. How does that help us? How does delta H of the reaction help us? What is delta H here? Yep, delta H will be equal to Q. So we can say directly that 250 joules per mole is being released from the system, right? The system is losing 250 joules per mole of energy. At the same time, during the reaction, the surroundings is doing work on the system. So if the surroundings is doing work on the system, is that going to be positive work or negative work? Yes, this is positive work. Right, and how I think about this, right? If the surroundings is doing work on the system, I think about going to get my hair done, right? Going to get my makeup done, something like that, right? If you go in and you get a haircut, then their surroundings, your barber, your hairdresser, right, is their surroundings. You are the system. You walk in and you get work done, and now you come out feeling better about yourself, hopefully, right? You look different. You had positive work done to you. You didn't do anything. You sat there, right? Someone else did work on you. So now you have more energy than to begin with. Okay, so that's going to be positive work. So delta E is equal to negative 150 joules over mole, because we can just add those two together. So that correlates to C.
For like formula's sake, can we always just leave it positive, and then if work is being done by the system, it's just plus a negative W?
Yes, yep. That's why I like to work with it that way.
He's overcomplicating it in lecture today.
Yeah, if you just think about it, right, heat plus work, and you're saying, okay, work is going to be positive because the system has work done to it. Or if you're saying, okay, it's going to be negative because the system is doing the work, then you can just say plus a negative or plus a positive. Yep, delta H will equal Q. This goes back to like Gen Chem 1 kind of explanations. So I think for this exam, you don't need to necessarily know why. But delta H will equal Q in these scenarios. Has to do with the systems and the surroundings and blah, 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 and how you identify stuff. But just know that delta H is going to be equal to Q, right? Your heat, thermal heat is going to be equal to heat in general. Any other questions on the homework? How are we feeling about this chapter? Is it feeling better, worse than the other ones? Only two more. Better? Okay, awesome. I think entropy and stuff is fun. I think it gets a little bit less complicated than all of the acid bases equilibrium stuff. Yep, so right, don't fall into that trap either, right? It I think Dr. Lindahl tends to try and make things harder than they need to be. But when you're going, so as you go through the practice problems of your homework, as you go through the practice exam, right, they seem easy, try to make them more complicated, right? Don't always follow them and make them straightforward. If you, right, look at question 12, right? Question 12, we were given all of our equilibrium constants and we needed to solve for G, right? Just straight up delta G. Do this problem again, but solve for one of the equilibrium values you're looking for, right? You know what delta G is now. You're given delta G standard, you're given R and T, and you're given your other delta G, or you're given your other Q values. Like, try and solve for the pressure of H2O at equilibrium. See if you can go backwards in this case and take out a different variable and see if you can still get that answer. Right, I think going forward can sometimes be the easiest way to see something, but it's working backwards that you might be like, I don't know how to do this, but you really do. It's just opposite of what you've been doing and practicing. Right, try to make them a little harder if you can.
Did you go over one of the practice problems in his notes?
Yep. I was just looking at that. Okay,
The very last one.
yep. So we're gonna go over practice problem 5 from the notes if anyone wants to do that along with us.
I think
I
there's
have
two
not,
separate parts of the problem.
yeah, I haven't done this, so I think we could just do the whole thing and then
Okay.
that'll probably help me with the second part too. Okay, so this is saying calculate delta G naught for the reaction. Okay, so we're looking for delta G naught. I do not have appendix 2. But for delta, so how you would solve this problem is the same way we solve for delta H and delta S in homeworks 13, 14, 15, right? There should be another appendix with a whole bunch of different values for delta G that you can plug in here. And it's going to be the same thing where it's delta G naught is equal to the sum of the delta G of the products minus the sum of delta G of the reactants. Okay, does that make sense how you would solve that first value of delta G? And delta G naught would be equal to negative 140.1. I would show you how, I just don't have appendix 2 because I don't have the textbook. Okay, but it's the same setup. You would have to multiply 2 times the value of SO3, right? You still have to do that. And then the 2 times the value of SO2. Okay. Delta G here is spontaneous or non-spontaneous? Yep, this would be spontaneous. Coolio. Okay, so the next part is a reaction occurs spontaneously at 72 degrees Celsius if the enthalpy change is 19 kilojoules per mole. What is the minimum of delta S for the reaction? Okay, how would we solve this problem? Right, we're saying it occurs spontaneously at 72. We know enthalpy, we're trying to find the minimum entropy. We want delta G to equal to 0. We're saying this reaction becomes spontaneous at 72. So that becomes spontaneous portion is when we're at delta G equal to 0. It's at that equilibrium portion. So delta G naught is equal to delta H minus T delta S. Delta G will be 0. So we can say that T delta S is equal to delta H. And delta S naught would be delta H divided by T. We know that enthalpy is 19 times 10 to the 3 joules over mole. And temperature, we have to convert to Kelvin. I don't have my calculator on me. I got, oh, I did the wrong thing. So this should be 345. Good question, Francesca. So we're going to set it equal to 0 because when a reaction becomes spontaneous, delta G is equal to 0. It's right at that equilibrium portion. And that's, you're either going to flip it to be positive if you go higher in temperature, or right, you can either go positive or negative from that 0 point. So when it becomes spontaneous, that temperature in which it becomes spontaneous is the last moment it's at equilibrium, or is the moment it's at equilibrium. And so we know that at equilibrium, delta G will be equal to 0. So we're looking for what is the minimum value of the delta S for the reaction when it's becoming spontaneous. That's why we need to set it to 0 here. Okay, so then we can say this, and I got delta S is equal to 55.1 joules per mole times Kelvin. Is that what we got? Okay, and then there's no questions on that one. The last portion of this is the sublimation. Yes, yep. So any value above 55.1 would make it spontaneous. So you could have 50, 56, 57, anything like that, or jump it up even higher. Sorry, let me explain that differently. So we're saying at any other, this would be the delta S for the reaction. At any temperature higher, then we're going to have a spontaneous reaction, right? It's becoming spontaneous at 72. So at 73, 74, 75, those would all make it spontaneous reactions. So the temperature is controlling spontaneity. Your delta H and delta S are going to stay the same, but it's that T component, that temperature component, that's affecting how delta S affects delta G. Yes, this is at equilibrium. It's when the reaction becomes spontaneous. Any values above this is when it's becoming when it is spontaneous, it is becoming spontaneous right now. It would be spontaneous with these values. Yeah. I know it's like very tricky, the wording of things. Okay, and then the last one is the sublimation of CO2 at negative 78 degrees Celsius is given by the equation CO2 solid goes to CO2 gas. Delta H is equal to 25.2 kilojoules per mole. We want to calculate delta S sub for the reaction in which 84.4 grams of CO2 solid was used. Hey, does anyone have any ideas how they would do this problem? Or what equations you might use in order to solve this problem? Ideas on how to solve it, equations you might use, or any concepts that relate to sublimation that are important. Okay, so what does it mean to sublime? What are we doing when we're subliming? Yep, we're going from solid to gas. And so what is that called? A what change? We're changing what about our system? Yep, we're doing a phase change, right? So sublimation is a phase change. What do we know about phase changes in terms of equilibrium? Are they at equilibrium for phase changes? Are we not at equilibrium? What's going on? Anyone have a guess? If we think about, if we think about our heating curves, right? At our flat portions, we have our phase changes. And if we think about our phase diagrams too, right? We always said that these lines are phase changes and we have equilibrium, right? At those lines, you can go forward or backwards. So at phase, so for phase changes, we're at equilibrium. Okay. So when we're at equilibrium, does anyone know of a special delta G equation that we can use? Yes, yes. So we can say if we're trying to find, right, if we're at equilibrium, we can say that delta G naught of the reaction is equal to negative RT ln of K. Because we know that at equilibrium, we're going to have some sort of K value. Okay. But how do we know what K is if we're just subliming, if we're just going from solid to gas? I think this is how you're supposed to do it. I have not tried this, so let me just. I might need to think about this one. I just tried something. I had a thought. I might need to try this one and get back to you on how to do it. If you give
When
me
I asked him after
yeah.
lecture, he mentioned something converting it to moles.
Yeah, so my thought process here is that right, we need to use this did he say you how to use this equation, Adrian? Did he give any hint to that?
No, he didn't really talk about it. He was just talking about the molarity about it real
Okay.
quick at the end of class.
Yep. So my thought here is that you have 84.4 grams. You need to convert this into the moles of the product that you have because you have right, you're going from solid to gas. So it's 12.01 plus 32 because you have CO2. 4.01 grams over 1 mole. Okay, so we have 1.92 moles of CO2.
I think he rounded that to 2, if I remember correctly.
Okay, so if he rounds this, we'll say we have 2 moles of this. Right, your KEQ is just your concentration of CO2. And I think part of me wants to use Pivnert to get the pressure. What would that do? That. Okay, so if we do that, we get that. And then we have negative. Okay, that's a negative value. And then if we subtract, 25.2 from this. We divide by negative. It's supposed to be. Nope, that doesn't help me. Okay, I think I need to stare at this a little longer.
I was gonna ask him anyways again tomorrow at his review session. He told me to ask him about it, so I'll let
Okay.
you know at that last minute thing tomorrow night.
Okay. Yeah, I'll try and figure it out. You definitely need to convert it to moles. You need to do something, right? Because if we're looking at right, we know delta H, and right, if we know this equation too, delta H minus T delta S. Right, we want to solve for delta S. So if we know delta G, right, we can subtract delta H and divide by delta T in order to find that. Oh, did I do that? Hold on. Let me try one more thing. Let me try it one more time. Because I might have screwed up my units 4 times. We have delta G naught of the reaction is equal to negative 8.314. What is, I keep on just typing this. And K can either be, if it's concentration, you can assume 1 liter, it would be 2. Or you could do Pivnert. We'll try 2 for now. See what happens. Negative 8.314 times 195 times the element of 2. Okay. Then we get delta G is equal to negative 1123.7. This is in joules per mole. So then we can say minus 25.2. It's that value. Negative, what did I say, 195 times S. Okay, so I'm getting closer. So, right, if you solve for this using, if you solve for this using, what is this, concentration, you get a lower value. So if you do PV is equal to nRT and solve for it this way, if you get pressure, if you assume 1 liter, you can do 2 moles times 0.08206, and your temperature is 195 over 1. You get a pressure of, I think, 32. Yeah. P is 32. So then this is your pressure at equilibrium of CO2. So then in your delta G naught is equal to a negative RT ln of K, right? K is now 32 because it's just your gas that's subliming. So delta G naught would be equal to negative 8.314 joules over mole Kelvin. Your temperature is 195 again, and you have your ln of 32. So let's try this. And we get delta G naught is equal to negative 5618.8 joules over mole. And then we can use delta G is equal to delta H minus T delta S. We know from our question that delta S is 25.5 kilojoules per mole. So we have 5618.8 joules over mole equal to 25.2 times 10 to the third joules over mole minus 195 times delta S. And I got delta S equal to 158. So it's still not exactly what he wrote, but I think it has something to do along those lines. I will still try and figure out how to solve this. Or Adrian, you can teach me how to do it tomorrow in the last minute review session. But the good news is that I haven't seen anything like this between the homework and the practice problems, or in the practice exam. So maybe this is just a really big challenge question. He's not going to actually ask you. But also figure out and try and figure out how to solve this and get back to y'all about it. This is in the PowerPoint question or PowerPoint that he posted for module 6. It's practice problem 5. It's the last slide in that PowerPoint. Sorry if anyone is thoroughly confused. I apologize. Just focus on the homework and the practice problems for right now. Or if you know how to solve this, send me an email, let me know. I'll be happy to look at your work, or you can teach me something today. Okay, any other questions between that we just tried to solve, or anything on the homework, or anything in chemistry related in general?
You also talk about the relationship between reversibility and efficiency.
In terms of like
G.
work, whatnot.
With delta G.
I don't think you need to.
Yeah, I guess you're right with it in terms of work.
Yeah, so right, your work, nothing can ever be 100% efficient, right? A lot of the machines we use today are like 30% efficient. So even though you have all of this work available to do, right? You release delta G, you have all this free energy. Not all of that free energy can be used for work. And so you can't 100% reverse a reaction because your efficiency is lower. Or using up that energy available is lower than what we expect it to be. Does that make sense?
I think so. He used like the example of a combustion reaction and how it's very efficient but not reversible.
Yes. Yep. So, right, think of it as like pushing a cliff or pushing a rock off of a cliff, right? Very efficient because it'll just fall, but it's very hard to reverse that process of lifting that boulder back up and putting it back on the cliff. I guess in terms of like a non-chemistry example.
So then it would have a very low free energy.
Yes. Yep. Does that help answer your question? A little bit, not really. Anything else, everyone? Do we feel more confident? Gigs all around. This is your second to last exam, in-class exam. Are you so excited? And you don't have another one for like a month, less than a month.
Do you know what you're gonna do for the final? Like, I'm guessing he'll give like probably a final review.
Yes, so I think y'all take them at different times. Like I think the 12:40 has it on Friday, and then the 3 o'clock has it on Tuesday. Is anyone representing both? I can confirm or deny my statements. So I guess in order to make it fair, I have to do a review session before the first final. So I'll probably do it that Wednesday. I'll still do one Wednesday. If the final's Friday, we'll do one Wednesday, for however long we need it. And then that'll probably be it for, I guess I could do the same thing, right? If the final ends up being Friday, which I think it is for the 12:40, that's the first one. Or it's the first final for someone. If that's the case where it's on Friday again, like usual, then we'll do a Wednesday review session and then a last minute one on Thursday. And that'll probably be it for my review session, so that like you just have to study on your own from there. If you have more time available to you. But I think that'll be my contribution. If I get bored when I'm home for sweet, I don't know where I pulled that out of. But if I get bored during Thanksgiving or sometime over the weekend, I'll try and throw together some additional practice problems for y'all. No saying if they're going to be easier, harder, or exactly on par with what he's going to put down for the final. But just general questions, just more practice. I can try and put together a couple of those from this semester, change up some of his problems and stuff too. I can try and do that for y'all for additional practice. I can also send out a poll or something if there's anything specific you want to see from me. Or I guess I can ask that now. Is there anything specific you want to see from me for the final?
You have like the data of like the most missed questions on the exams, or like can you pull from exams?
I can ask him if I can do that because I know like which questions get missed a lot. I know like in one of the past exams, very little got from one version, a very small percentage got the actual answer. So I can kind of look at those and try and either revamp them just so that they're like different from different numbers and whatever from his questions, and or a slightly different question and still kind of keep it the same. But I can try and pull some information from there and see if he'll let me release that to y'all for some additional practice. That might just take me a minute because there's 4 exams and 7 exams, 4 versions for every 7 exams. But yeah, I can try and find something like that.
Okay, thank you.
Yep. Anything else people want to see? You could take a moment in a couple days and let me know if there's something specific, but focus on this exam, right? When you're bored this weekend or something, you can let me know what you want to see from the final. And I'm happy to do that review for you. Anything else for me for tonight? Okay, y'all, it's been wonderful. Thanks again for being flexible. You'll see me in my crippled self on Friday. And then I'll send out a Zoom for tomorrow. If you have any last minute questions, we'll stay here for the hour. And if no one's done, we'll end early and you can go to bed. But great. Thanks so much. Thanks for coming. Thanks for stopping by. And I'll see you tomorrow or Friday. Thank you. And I'll post this when it's all done as well.
Miss Allison?
Yep.
I'm sorry, can you go to number 7 again? I just have a quick question on it.
Absolutely.
So if that were to say spontaneous reactions would violate the second law if the entropy change of the system were positive, is that true?
I still don't think so. I don't think we can I don't think you can violate the second law,
Okay.
like
Because
technically.
I think he was talking in class one time. They were like scientists or somebody were trying to violate it, but then they made like a law. I don't know. It was something like
Yeah,
that.
I think there's something in the notes where he's like the second law of thermodynamics, can it be yeah, here it is. Can the second law be violated? In principle, yes. In practice, no.
Okay. So if that were to
Well,
say in principle or somewhere in that said principle, then it would have been.
yeah, in
Okay.
principle, can the second law be violated? This, or like if it says in principle, the second law can be violated. Period. Right? True or false? Can it be violated? Yes. Right.
Because yeah, he did a bunch of those where it was like a glass of water with ice, and then over time it melted. He said,
Yes.
"Can it go reverse?" In principle, it can reverse,
Yes.
but in practice, it like will never happen.
Yep. Right. You
Okay.
could. It's like kind of the same thing where it's like if you walk into a wall enough, eventually you will
You'll go through it.
go through it. Right.
Yeah.
Right. If you let it go long enough, eventually the ice will freeze. But we're not here long enough to see.
Then
So yeah, in principle, yes, it can be violated. In practice, it will not.
perfect. Then for number 3, it says the heat generated by a system can only be used to do work if there's a temperature gradient.
Yep.
So that's just because you're moving from temperature to temperature, it's doing some sort of work.
Yes. Yep. So if you right, if you're both my hands are at the same temperature right now, so I put them together, nothing is going to transfer because they're at equilibrium, right? Nothing
Okay.
back and forth. If this one was super hot, this one was super cold, I would put them together and eventually they would get to the same temperature because this one is now transferring its heat to this one.
But it says only, so it can only work with a temperature, like nothing else can do it.
Yes. Yep. It only works if there's a temperature gradient.
So work is directly related to temperature, I guess.
So it's saying that right, the heat generated can only be used to do work if there's a temperature gradient, and that's because right as this thing's getting hot, this thing is getting sorry, right, cold and hot. If the cold thing is getting hot, that means that the hot thing is releasing heat.
Is doing work on it.
Yep. So that
Okay.
heat that it's releasing is doing the work on that colder item.
And if it was opposite, it could make the colder one could make the hot one cold. Would that still be work or
So no, right, because it only flows from hot to cold.
hot to cold because second law?
Yes.
Okay. Okay.
Yep.
Perfect. All right.
And-
Thank you so much.
Yeah, of course. Anything. Have a great night. Anyone else? Have a great night, everyone.